Welcome back to another episode of the Future of Data Systems. Today, we're diving into some really interesting concepts surrounding distributed data processing, the challenges of ensuring data correctness, and how data architecture is evolving. Whether you're a seasoned developer, a data scientist, or just someone curious about how data systems really work, there's something here for you. So grab your headphones and let's jump right in. Let's start with distributed execution and how it can enhance complex queries. Imagine you need to analyze data spread across multiple partitions. Traditional methods might struggle with this, but stream processors like Storm provide a solution. They allow us to utilize message routing and partitioning to compute results efficiently. For example, Storm has been used to track how many people have seen a particular URL on Twitter, which involves combining follower sets from various partitions. This really showcases the power of distributed execution. Now, when we think about assessing the legitimacy of transactions, like figuring out if a purchase is fraudulent, we need data from various sources. You might examine reputation scores linked to a user's IP address, email, and shipping details. Each of these datasets is partitioned, so gathering the necessary scores requires performing multiple joins across these partitions. While stream processing is a powerful tool for large-scale applications, sometimes it's more straightforward to use a database designed specifically for multi-partition joins. Moving on to a critical aspect of data systems, reliability and correctness. For decades, we've relied on foundational properties of transactions, atomicity, isolation, and durability, to ensure our applications behave predictably, even when faults occur. But here's the kicker. These properties can be more fragile than we realize. Weak isolation levels can lead to unexpected behaviors, especially under high concurrency or failure conditions. Take the Jepsen experiments, for instance. They've uncovered significant discrepancies between what some systems claim regarding safety guarantees and their actual performance during network issues or crashes. Even with a robust database, your application code has to effectively leverage its features, which can be tricky, especially if the configuration is complex. If your application can tolerate occasional data corruption or loss, you might find things a bit easier. But for those who need stronger assurances of correctness, traditional methods like serializability and atomic commit come into play. However, these approaches often limit scalability and fault tolerance, particularly in geographically distributed architectures. So, how do we conceptualize correctness in data flow architectures? One idea that comes up is exactly once semantics. This means that if message processing fails, you can either drop it, risking data loss, or retry it. But what if the operation was successful the first time? That could lead to duplicate processing, which is definitely not ideal. To address this, we can use idempotent operations. An idempotent operation ensures that no matter how many times it's executed, the outcome remains the same. However, transforming a non-idempotent operation into an idempotent one can be quite challenging, often requiring additional metadata and careful management during node failovers. This leads us to a common scenario. Consider a money transfer operation. If the client retries the transaction after a timeout, it could inadvertently double the transfer amount if the operation isn't idempotent. Real-world banking systems have evolved to handle these complexities, but it's crucial to understand that relying solely on database transaction mechanisms isn't enough. We need to consider the entire flow of requests from the client to the database. One effective strategy is to generate a unique identifier for each operation, like a UUID, and include it in the request. This way, if the request is submitted multiple times, the database can recognize the duplicate and prevent the operation from executing more than once. This approach enforces a uniqueness constraint within the database, helping to maintain data integrity even under challenging conditions. Finally, let's consider the end-to-end argument. a principle articulated back in 1984. It suggests that certain functions in a system are best implemented at the endpoints rather than in the middle. This principle can guide us in designing more resilient and efficient data systems. As we wrap up today's episode, we've explored the complexities of distributed data processing, the importance of ensuring correctness, and the innovative strategies we can use to build reliable applications. The landscape of data systems is always evolving, and grasping these core concepts is essential for anyone looking to navigate this space effectively. Thanks for tuning in to the Future of Data Systems. If you enjoyed today's discussion, don't forget to subscribe and share it with your fellow data enthusiasts. Until next time, keep questioning, keep learning, and keep pushing the boundaries of what's possible with data.